Let's look at some real examples of probability distribution functions and data distributions in general, and kind of wrap your head around a little bit more about data distributions and how to visualize them and use them in Python. So go ahead and open up the distributions IPython notebook file from the course materials, and you can follow along with me here if you'd like. Let's start off with a really simple example. So a uniform distribution just means there's a flat constant probability of a value occurring within a given range. So we can use this by using the numpy random.uniform function, and this call says I want a uniformly distributed random set of values that ranges between -10 and +10, and I want 100,000 of them. And if I then create a histogram of those values, you can see it looks like this. So there is pretty much an equal chance of any given value or range of values occurring within that data. So unlike the normal distribution where we saw a concentration of values near the mean, a uniform distribution has equal probability across any given value within the range that you define. So what would the probability distribution function of this look like? Well, I'd expect to see basically 0 outside of the range of -10 or beyond 10. But when I'm between -10 and 10, I would see a flat line because there's a constant probability of any one of those ranges of values occurring, okay? So a uniform distribution, you would see a flat line on the probability distribution function because there is basically a constant probability. Every value, every range of values has an equal chance of appearing as any other value, okay? And that does happen sometimes. Now we've seen normal, or also known as Gaussian, distribution functions in the past and already in this course. You can actually visualize those in Python. There is a PDF function on the scipy.stats.norm package function. So here in this example, let's just walk through what's happening here. We're creating a list of x values for plotting that range between -3 and +3 with an increment of 0.001 in between them. Okay, so those are the x values on the graph. And then we're going to plot the x-axis, and the y-axis is going to be the normal function, norm.pdf, probability density function for a normal distribution on those x values. And we end up with this. So the PDF function with a normal distribution looks just like it did in our previous slide. That is a normal distribution for the given numbers that we provided, where 0 will represent the mean, and these numbers are standard deviations. Now, to actually generate random numbers with a normal distribution, we've done this a few times already, but just as a refresher. Again, if you use the NumPy package, it has a random.normal function, and the first parameter mu represents the mean that you want to center the data around. Sigma is the standard deviation of that data, which is basically the spread of it. And then we specify the number of data points that we want using a normal probability distribution function. Okay? So that's a way to use a probability distribution function, in this case the normal distribution function, to generate a set of random data. We can then plot that, just show a histogram broken into 50 buckets and show it, and that's what we end up with. And it does look more or less like a normal distribution, but since there is a random element, it's not going to be a perfect curve. You know, we're all talking about probabilities. There's some odds of things not quite being what they should be. Another distribution function you see pretty often is the exponential probability distribution function, where things fall off in an exponential manner. So when you talk about an exponential fall off, you expect to see a curve like this, where it's very likely for something to happen, you know, near 0, but then as you get farther away from it, it drops off very quickly. So there's a lot of things in nature that behave in this manner. And to do that in Python, just like we had a function in SciPy stats for norm.pdf, we also have an expon.pdf for an exponential probability distribution function. And we can do the same syntax that we did for the normal distribution with an exponential distribution here. So again, we just create our x values using the numpy a range function to create a bunch of values between 0 and 10 with a step size of 0.001. And then we plot those x values against the y-axis, which is defined as the function exponential PDF of x. And it looks like that, an exponential fall off. We can also visualize probability mass functions. It's called the binomial probability mass function. And again, same syntax as before. So instead of expon or norm, we just use binom. And again, a reminder, probability mass function deals with discrete data. And in this case, we are dealing with discrete data. We we have been all along, really. It's just how you think about it. We're creating some discrete x values between 0 and 10 at a spacing of 0.001. And we're saying I want to plot a binomial probability mass function using that data. And with the probability mass function, I can actually specify the shape of that data using two shape parameters, n and p. In this case, it's 10 and 0.5. And if you want to go in and play around with different values to see what effects it has, that's a good way to get an intuitive sense of how those shape parameters work on the probability mass function. Lastly, the other distribution function you might hear about is a Poisson probability mass function, and this has a very specific application. Looks a lot like a normal distribution, but it's a little bit different. The idea here is if you have some information about the average number of things that happen in some given time period, okay, this can give you a way to predict the odds of getting some other value instead on a given future day, okay? So as an example, let's say I have a website, and on average I get 500 visitors per day. I can use the Poisson probability mass function to estimate the probability of seeing some other value on a specific day. So let's say I get an average of 500 visits per day. What's the odds of seeing 550 visitors on a given day? That's what a Poisson probability mass function can give you. So in this example, I'm saying my average is 500 mu. I'm going to set up some x values to look at between 400 and 600 with a spacing of 0.5, and I'm going to plot that using the Poisson probability mass function. And I can use that graph to look up the odds of getting any specific value that's not 500, assuming a normal distribution. So 550, it turns out, comes out to about 0.002 is the probability there, or 0.2%. Very interesting. All right, so those are some common data distributions you might run into in the real world. Pop quiz. Just make sure you're paying attention. What is the equivalent probability distribution function when using discrete instead of continuous data? So remember, we used a probability distribution function with continuous data, but when we're dealing with discrete data, instead we use, hint, it's right on the screen right now, a probability mass function. Okay, let's move on. So that's probability density functions and probability mass functions, basically a way to visualize and measure the actual chance of a given range of values occurring in a data set. Very important information and a very important thing to understand. We're going to keep using that concept over and over again. So make sure you watch this video again if you have to. You're good? All right, let's move on.